Morning. This talk is just a big joke. Also, thank you for the SCRT team for having me again, and thank you for the pate, and thank you for the magazine that is at the origin of this joke. So I'm going to talk about quantum, cyber, blockchain, IoT, and maybe more, and I'll start with quantum. Quantum, as in quantum computing, you probably have heard about, well, the infinite power of quantum computers. I would like to say a bit more about it and how it relates to cybersecurity, how it relates to blockchain and IoT. So if you look for quantum computer pictures, you will see this kind of stuff. Where's the clicker? Okay. But obviously it is not a quantum computer, so I kept searching and I found this. So do you know what it is? Doesn't look very quantum, but if you look at the description, it explains. I don't know if you can read the text here. So it's quantum scalar pendant energy card, and it resists radiation. It also reduces your inflammation in your body. It helps protect your DNA, whatever that means. It improves your stamina, endurance, strength, and probably libido as well. It increases your energy, blood circulation. Does it cure cancer? I don't know, probably. But there's something, if you read correctly, there's something that it doesn't do. It does not break any crypto or cyber or blockchain, so it's mostly useless for us. So the kind of quantum computer that we'll be interested in is more like this. It's the big fish will be the quantum computer that will try to eat the small fish. And we're going to see how powerful this fish, the small fish, is and how we can defend against the big one. So, okay, mathematics. I just want to explain you very briefly the principles of a quantum computer. I'm not going to give you all the math background, but just the high-level idea. So instead of working with bits 0, 1, the quantum computer, as you probably know, it works on quantum bits or qubits, which in some sense can be 0 and 1 simultaneously at the same time. So this notion of simultaneously, or which is called superposition, is characterized by two values if you have one qubit. So these two values that I note alpha and beta here, they are called the amplitude. You can see these amplitudes like the parameters or the probabilities associated to your quantum bits. So if you observe your quantum bit, which is in a state of superposition, you will see a 0 with probability alpha square, and you will see a 1 with probability beta square. So the difference with what you're used to is that alpha and beta are not just numbers between 0 and 1, they are complex numbers that can be negative. So if you have a complex number, you have an imaginary part possibly, and you can take the modulus in and square it in order to get a probability. So fundamentally, that's what a qubit is equivalent to. So you can perform quantum gates on this qubit, which is different from a normal logic gate. So if you have a single bit on top, so you have a bit as an input and a bit as an output, classically. In the quantum case, it's a bit different here. So instead of having one value, 0 or 1, you have two values. So you have the probability of being 0 and the probability of being 1, essentially. And you have a gate, which transforms this set of two probabilities into another set of two probabilities. So in this case, we have, where's the 1 and 0, I don't see the fucking laser, okay, whatever. So you have 1, 0, it means that it will be 0 with probability 1, it will always be 0, and the 0 that you see in the bottom of the vector means that it has a chance 0 of being 1. Now if you apply this gate, which is called the Hadamard gate, the probabilities, the quantum probabilities will be 1 over square root of 2 and 1 over square root of 2. It means that if you square these values, you will get 1.5, 1 over. So you will have a chance 1 over 2 to see 0 and a chance 1 over 2 of seeing 1. So you've gone from something deterministic to something probabilistic. And that's the magic of quantum computing. It gets you real randomness. Okay, but the bottom line is you get two numbers instead of 1. So if you generalize this, instead of having just one qubit, if you have n qubits, so you have 2 to the n possibilities. So each possibility is associated to one probability, so you will have virtually 2 to the n numbers to deal with. Okay. So in the case of 2 qubits, you will have 2 to the power of 2 equal 4, and 4 values here, 0, 1, 0, 0. Okay. So the point is that you will also need, so matrices, theoretically, a quantum gate is just equivalent to multiplying a vector with a matrix. It's equivalent. It's not exactly what happens physically, but you can simulate it. You can simulate a quantum computer by just doing matrix vector operations. Okay. And why it works and why it's so powerful is that you cannot simulate this on a normal computer. Well, you can perform a matrix vector product, but as the number of qubits grows, if you have, for example, 50 qubits, you will have to manage 2 to the power 50 numbers, which becomes infeasible. So maybe 40, 50 becomes to be the barrier where you cannot simulate it. So nature gets us this power that if you have n qubits, nature will magically perform computations that are equivalent to dealing with an exponential number of probabilities. Okay. And so I'm almost done with the boring theoretical part. Nobody's sleeping, it's good. So this power, this new type of computing, we don't really know why, but sometimes for certain problems, it can find the solution much faster than a classical computer. So not faster in terms of, the operations are done faster per unit of time, but in the sense of theoretical complexity. For example, instead of having an exponential complexity on a classical machine, on any classical machine, the quantum computer will allow you to run in linear time, so in time proportional to the size of your problem. So for cryptographers in complexity theories, when we hear exponential, we hear impossible, and when we hear polynomial or linear, we hear practical, feasible. So a quantum computer can get you from the impossible to the possible, which can have some benefit. So what quantum computer is not? So like I said, it's not something that's going super faster than normal computers. So I used to have a dishwasher that had the label quantum, and I think what the vendor meant is that this dishwasher was somehow washing my clothes faster than another one. But in the case of computers, quantum doesn't mean faster in terms of frequency. You sometimes hear that because a set of qubits is somehow a record of all the values at the same time. Sometimes people simplify this and say, oh, it computes all the n squares in parallel and picks the best one at the end. So there's something called quantum parallelism, but it's very different from this naive notion. And last but not least, it's not something that will magically solve any hard problem. So when you hear about hard problem, it's typically the class of NP problems, so problems for which the solution can be easily verified. And in particular, the NP-complete problems, and more generally the NP-hard problems, are those problems for which finding a solution is extremely hard, is impractically hard in the sense of exponential, but for which once you have a solution, you can verify efficiently whether or not it's the correct one. So bottom line, quantum computers will not solve these types of problems. But so okay, maybe the main reason why I'm here today is because of this guy, Peter Shor. I think in 92 or 82 or 84, sorry, he found a quantum algorithm. Sorry, but we don't have quantum computers yet, but we know how it works, so we can write papers about it and become famous. So he wrote a paper where he explained how to go from the number n to the factors p and q, where p and q are prime numbers. And the same algorithm can be applied to finding the exponent d if you have a value x raised to the power of d modulo p. Well, this problem is called a discrete logarithm in math, in cryptography. And the hardness of finding the small d here is behind the security of most of our internet connections. So if you look at TLS, SSH, which uses elliptic curve cryptography, and Diffie-Hellman, all the security of these problems is based on just this stupid equation. So classically, with normal computers, fortunately, we don't know how to solve this efficiently. We don't know how to factor big numbers. We don't know how to solve discrete logarithms. So the complexity is essentially exponential, to simplify. But with the quantum computers, it will be cubic. So all the n to the power of 3, which means feasible, which means that RSA is dead, Diffie-Hellman is dead, elliptic curve is dead, and it's time to put manic because all our connections that were encrypted would become broken, which is bad. So yeah, there might be reasons to panic, and some people do not necessarily panic, but some people would like you to panic. Okay, but so what's the deal actually? Should we, ditch our old RSA crypto and get some new type of crypto? So concretely, how easy would it be for a quantum computer to break the crypto? So based on the information we have today, some researchers tried to estimate how long it would take, how big would the computer be. And they estimated that to factor an RSA modulus of 1024 bits, which is relatively low today, it would take of the order of 1 million qubits. So several orders of magnitude more than the size of the number. And to factor an RSA 2K 2048, they estimate in terms of latency that it would take a few months, so specifically 5 months in this example. So it would not be just, in a few seconds. It's not as bad as it sounds. To summarize the state of the research today, the best quantum computers we have, if we can call them like this, they have of the order of 10 qubits. So it depends on how you read the press release by IBM and Google. Sometimes they would say 50 or 70. It's not really a quantum computer, it's just a bunch of qubits that may or may not do anything. But anyways, number of bits we want to attack in RSA, in ECC, is of the order of a few hundreds or thousands. But the number of qubits we'll need is way above this, few millions. So why millions and not just thousands? Because a quantum computer is very fragile. There's a lot of errors and interference happening, and we need to correct the errors. And to correct all the errors that are happening inside a quantum computer dynamically, we need many, many more qubits. Okay. So where are these crypto algorithms, RSA, ECC, where are they used, and where might there be a problem? So in blockchain, obviously, the old crypto TLS SSH, it's the past, the blockchain is the future, it's disrupting the industry, and we all love blockchains. So yeah, there's no Lambo today. If you invested in crypto, you must be rich. So I won't spend days explaining what a blockchain is. If you know, good for you. If you don't, I'm sorry. But it's essentially a database, but it's even less useful than a database because you cannot remove data from this database. So it's also immutable, and it's a database that is not distributed like all the stuff we heard about by Apache and others in the early 2000s. So now the new world is not distributed, it's decentralized. So it also happens to be distributed, but the main value is that it's decentralized. There is no single authority having the power to manage this database. So there are these consensus protocols that everyone can agree and solve this Byzantine fault tolerance problem. And it's consensus protocols. We have different types of consensus protocols, proof of work, proof of stake, but it's not the point today. We're talking about security and how it relates to quantum computers. So do you think blockchains are quantum resistant? Do you think quantum computers can break blockchains? Yes, no opinion? Oh, yeah. Yeah. So typically, if you use a cryptocurrency, which most of the time use a blockchain, you will have one account. And what is your account technically? What is your wallet? It's not really bits that represent money. It's most of the time it's a secret key. It's a secret key that is associated to a public key. So your address, the value that people can use to send you money, is essentially a public key, and the number that you use to unlock this money to spend it will be your secret key, and you have to keep it secret because you don't want other people to spend your money on your behalf. Okay. So if you look at Bitcoin, typically, the secret key is an elliptic curve secret key for the elliptic curve sec 1P256K1. Never heard about it because only Bitcoin uses this curve. But the upshot that is that it's using elliptic curve crypto. It's using ECDSS signatures. It's using the discrete logarithm. So this problem that I mentioned before is broken by a quantum computer. So wallet security would be dead if we had a quantum computer. Now, what about mining? It's a bit less obvious. Mining is essentially a decentralized lottery where people create new money out of thin air using either proof of work or proof of stake, which are kind of equivalent but not completely equivalent. So you might think that proof of work is generally based on computing hash functions, and hash functions are not really broken by quantum computers. But both proof of work and proof of stake, as they are used today in most cryptocurrencies, they use digital signatures. So they would also be broken if we had a quantum computer. So bottom line, many blockchains would be broken. Okay. But there might be a solution. Something called post-quantum encryption. It looks like this, like you're in the Matrix. There's green letters and dark background. It looks very interesting. So post-quantum, it's just crypto, just a new type of crypto that would not be broken by quantum computers. So if it's not broken by a quantum computer, it must not use RSA, it must not use Diffie-Hellman, it must not use any problem that would be broken by a quantum computer. So no factorization, no discrete log. Okay. So example, RSA is not post-quantum, obviously, because it will be broken, but AES is post-quantum because it would not be completely broken. It would just be half broken, if you will. If you had a key of 128, it would get you security roughly 64 bits. We don't really know, but people like to say 64 bits because it's just the half, and it's the theoretical estimate. So people, have different opinions on when a quantum computer will come, if at all. I usually present this like an insurance. So like you buy an insurance to protect your house against flooding, against, I don't know, alien attacks, even though you know that is very unlikely to happen, but maybe you feel better when you have this kind of protection. So here it's, again, a risk management thing. You are a CSO, you have a budget to manage. Do you want to protect your organization against the risk of a quantum computer? When you are completely clueless about when a quantum computer will exist, some people tell you never, some people tell you tomorrow, you just have no way to decide. But more concretely, people like to listen to NSA. They tend to have interesting opinions on crypto. And I think 3 years ago in 2015, they published a memo via another organization where they said that they plan in the future, they don't say exactly when, in the future, they want to transition from normal public key crypto to post-quantum crypto in US federal agencies. And when they published this, there's all the conspiracy theories, people thinking, oh, NSA, they're up to something, they have quantum computer in the basement, or they know something that we don't. Well, my personal opinion is just that it's risk management again. If you know how much time it takes to deploy something new in a public agency, it might well take 30 years to switch from the old crypto to the new crypto. So maybe this is just being prudent and risk management. So if you want to see how the post-quantum crypto of the future might look like, you can go to the website of this project by NIST, which is the standard agency of the US government and de facto the standard agency of the whole universe. They just started a competition in the sense of a public project where anyone could submit their new proposals of a cipher. So even I did. And since November, there's a public list of 82 or 84 submissions that people propose. And in a couple of years, NIST is going to hopefully select one or more, which might become the post-quantum crypto of the future. Okay, so this kind of projects, it's funny for cryptographers, it's like destruction derby. So you submit your algorithm and you try to destroy the others while the others try to destroy you. And at the end, someone survives. Okay. So I'm not going to explain how this type of crypto works. It's pretty complicated. Even now, I don't really understand most of it. But you can just see it as 5 different types of crypto. The first one is based on something from the 70s, error correcting code. It's code-based crypto. The second type is also based on something from the late 70s by Leslie Lamport and others, hash-based crypto. It's essentially a bunch of binary trees and hash functions. Latest based, it's much more mathematical and much more interesting, maybe from a theoretical point of view. And most of the submissions are of this type, be it encryption schemes or signature schemes. Multivariate is also as old as mathematics. It's based on the harness of solving algebraic equations. So the kind of equations where instead of having just additions, you have additions and multiplications. And isogeny-based crypto, nobody really understands how it works. So very quickly, hash-based crypto. I'm going to show you the most ridiculous crypto construction ever. It's a signature scheme, but you can only sign one message. And this message can only be 1 bit. It can be 0 or it can be 1. So in this kind of construction, the private key, you will have 2 values for the private key, K0 and K1. So your private key is the pair K0, K1. And when you want to sign a message, so remember that a message is either a 0 or a 1. Let's say you want to sign the message 0. So your signature, you don't have to compute anything. It's just the value K0. K0 will be your signature. And how will the signature be verified? It will be verified because the public key will be the hash, where h is a hash function, will be the hash of K0 and the hash of K1. So someone who knows your public key, you know that this value is the hash of K0, then they can compare the value of K0 that you sent, or they can hash this value and compare it with the value they have, and they can verify that the value you sent, K0 you sent, is related to the public key they know. So it's so simple, it's so ridiculous that it's super hard to figure out that it's a signature scheme. It doesn't look like signing. The first time I saw it, I was like, the fuck is this? It's not a signature scheme, it's just nothing. And it's mostly useless, because you would need n keys for n messages of 1 bit, so it's totally useless. You can modify it a bit, but there's actually one place where it's used. There's a small trick to sign messages which are a bit more than 0 and 1, which are, for example, between 0 and 255. So you can sign a byte, for example. And if you can sign a byte, you can sign several bytes. So it's used in IoT blockchains. That's exciting because this IoT blockchain is, I was giving a training a few days ago, and literally every couple hours, we are going back to this IoT construction because there's so much discussion about it lately. So it's the backbone of IoT. Also, let's say it's scalable, decentralized, modular, no-fee. It's a blockchain, there's no block, there's no chain. So it's not really a blockchain, and still it's a blockchain, but it's better than the blockchain, or that's what they claim. It's new distributed ledger. It's designed for the IoT. Well, this is marketing. You may or may not like it. Okay, this thing is dead. Okay. Well, you might be skeptical, you might buy it, but yeah, that's interesting construction. Well, the upshot is that this IOTA thing, they use precisely the stupid crypto that I mentioned before. So stupid in the sense of super simple, but also in the sense of post-quantum. And so instead of using a crypto that is broken by quantum computers, they use this construction, which is not broken by quantum computers because it uses hash functions, and hash functions are not broken by quantum computers. So IOTA is safe against quantum computers. We can all sleep well even if there's a quantum computer tomorrow. But the question, is it safe against classical computers? So you might say, well, a quantum computer is just a generalization of classical one, so yeah, idiot, it should be safe. Well, no, not exactly. So what people found is that the security of their signature scheme was a total disaster. A total disaster in the sense that when you sign a message, you don't directly sign the message. You first hash the message, and then you sign the hash. Because the signature schemes we know, they can only take a value of a small size, typically maybe 256 bits. So you would first take your favorite hash function, you would take a secure hash function like Blake2 or SHA-2 or SHA-3, you would get a hash value as an output, and you would sign the hash value. But what IOTA was doing, they created their own hash function, which was called curl, like the network utility. And this hash function was completely weak in the sense that you could find 2 different messages which give the same hash value, so which is called a collision in cryptographers' terms. So if you can create 2 different messages that hash the same value, and if you can control this, then you can probably attack the scheme. So for example, if you sign the message, the transaction saying, oh, I want to send $10 to JP, and then I modify this message into I want to send $10,000 to JP. And since you computed the hash of the first one, you signed the first one, but the second one, the $10,000, has the same hash function, I can maybe send this transaction over the network and I will receive $10,000 instead of just 10. Okay. So from a cryptographer's perspective, this hash function was ridiculously weak, and therefore the signature scheme as a whole was also ridiculously weak. So everybody was pointing fingers at Toyota, you stupid idiots, you're just using a weak hash function instead of a strong one. But if you really try to exploit it concretely and steal people's money and not create money out of thin air, it's not completely straightforward. And that's the context of this big discussion we had on Twitter a few weeks ago with people shouting at each other. It was very, very violent at some point. People of IOTA saying, oh, it's not broken. IOTA is not broken because you can steal my money. And the crypto people were like, well, it's broken because it's broken. So the discussion was quite impossible. Well, still it was a good idea maybe to use post-quantum post-quantum crypto in the blockchain. So IOTA is not the only one claiming to do IoT for blockchain or blockchain for IoT. I don't understand. There's some reports saying that the Internet of Things and blockchain tech are made for each other. So blockchain and IoT, 4 important benefits of combining these two mega trends. So not just a trend, a mega trend. So even IBM says that blockchain and IoT are the best friends. Well, okay, so I'm skeptical. You know, it's marketing. We'll see what happens now in 10 years. Okay, so let's forget IOTA for a while and move to other blockchains which do have a block and do have a chain, so, but are not IoT. So cyber security of blockchains. So do you think blockchains are secure? Yes, of course they are. Of course they are. So I did quite a few audits of blockchain stuff since about a year or so, looking at the security of wallets, of consensus protocols, of validations. So it's sometimes people say, oh, blockchain people are just a bunch of idiots, they don't know what they're doing. So several times they don't know what they're doing business-wise. There are some types of security is sometimes a bit scary. It's not always as bad as I imagine when I started your audit, but it's not, to be honest, it's not as strong as it should be because you literally have billions of money protected by this code. And I think they should do a better job, hiring people like us to secure their blockchains. Just a very few examples, there's many more. I will not talk about Ethereum, but if you look at Bitcoin is surprisingly, the Bitcoin software is surprisingly okay in terms of security. So maybe the worst bug was in 2010, and it was a stupid integer overflow. So when you have a blockchain transactions, you have a bunch of inputs, you have a bunch of outputs, and the sum of the inputs should match the sum of the outputs. And the problem in this case was that the sum of the inputs could overflow the integer storing this number. So instead of having a big integer, you would have a very small one or negative one. And this could be exploited to create 1,084,000,000 for many bitcoins, and they solved it. They fixed the problem by adding this check, and so it was patched, and there was a soft fork, and then everybody was happy because the stolen money, the created money, could not be used after that. So I think it's probably the biggest known Bitcoin bug, but otherwise it's not. There is something really, really bad. Something I found last year, and that, it's really sad from my point of view. So maybe you know that, how much time do I have? Okay. In cryptography, when we talk of cryptographic security, you might hear the words, for example, 128-bit security. So what does it mean, 128-bit security? It means that breaking this crypto would take of the order of 2 to the power 128 operations, whatever the operations are, but this order of magnitude. We usually say that 100 bits is, it's okay, but not really what you would like to sleep well. 80 bits is not enough for long-term security, and 64 bits is usually perceived as very weak. If you take the attack on SHA-1 that people at CWI in Google implemented last year, so they found a collision for SHA-1, and I think the number of operations that was performed using Google GPUs and other machines was of the order of 2 to the 70 operations. So this order of magnitude. Okay. So now I looked at Lisk one morning, I was bored, I said, okay, I feel like breaking some blockchain this morning. Maybe I was too optimistic, but I just got lucky, I guess. I started looking at the code of this blockchain. I want to understand how they sign transactions and how was someone's secret key related to an address. So the first thing that I found was that the address was only 64 bits. And the address of 64 bits was derived from a passphrase. So you start from a passphrase. From the passphrase, you get a private key, which is your secret key. From the private key, you get a public key. And from the public key, you get an actual address of 64 bits. So what I could quickly find is two different passphrases, so essentially two different accounts, that could give the same address, so a collision. So to find a collision over 64 bits, you just need of the order of 2 to the 32 operations. It was relatively slow because of the algorithm they used, but it took me maybe 1 hour on 8 course to find a collision. So what I could do is create one account. So I create one account of this cryptocurrency and then receive money on this account, and then using the second passphrase, log another machine and hijack this account and steal the money of this account. So the first guy with the first passphrase lost access to his money. And what I found is that instead of just finding a collision, which take 2 to the 32 operations, you can attack any account by computing a pre-image attack, which would take you 2 to the 64 operations, which is much higher, of course. But I found several accounts holding millions of dollars worth of money, for which I could have computed a pre-image, so find another passphrase that gives the same address, and I could have stolen these guys' money, just because the address was too short. And well, I didn't do it. I still have my shitty car. I didn't buy a Lambo because I'm honest. Well, also because I was lazy. I estimated that it would have taken a budget of maybe $50,000 of EC2 and other cloud instances to get millions of dollars worth of money within 1 or 2 months. Okay, so I didn't do it. But they responded, the response was like, oh, but it would still be months of computation. Well, that's hard to do, so yeah. And this is still not patched. The only thing they did is warn the users and explain to them how to mitigate, how to protect their account. But there are still a bunch of accounts that are vulnerable. So if you have time and money, you can. Okay, no, I didn't say this. Okay. Another very funny one. So if you're into web security, you know that you cannot trust code client running on the client. And this one was really funny because this cryptocurrency, instead of doing all the verifications on the server side, on the side of the validator, it was trusting the client in verifying the transaction, for example, the signature. So verify that you have enough money to spend this amount of money. So the client was supposed to run this code checking that, oh, I want to spend $100. Do I have $100 to spend? Yes, no. But what you could do is, well, if the code is running on the client, you can just modify this code and bypass the verification. So yeah, that was a major disaster. Okay, so I think I'm almost done. I've talked about quantum, I talked about cybersecurity, blockchain, IoT. So what is missing here? Machine learning. Well, I said that I wouldn't have enough time, so I will only give a few highlights. So you should know that blockchain, AI, and machine learning, because it's completely different. And IoE, do you know what IoE is? It's even better than IoT. It's Internet of everything, not just things, all the things. And it will make you money in 2018. They don't have no clue how. And here they explain how IoT, blockchain, and machine learning are working together, they're best friends, to seriously innovate supply chain management, of course. And big data as well. So, well, big data was like 3 years ago, but you still hear about it. Big data powering blockchain with machine learning to revolutionize the IoT, cyber transportation, and logistics learning. And quantum as well. You can combine blockchain, AI, and quantum computing. It's the perfect whatever. Yeah, so much bullshit. So I practiced this presentation a few days ago with my friend, and Philippe, he said, "But what's the message of your talk?" I'm like, "What? I don't know. So maybe you can get your own takeaway of this talk, which is essentially a big joke." Okay, so thank you, and you can join my ICO GPK, and I still have a lot of Monopoly money to send if you're interested. Thank you very much. I can take questions.
Do you have any questions?
Okay, I have a question. When do you think will a quantum computer exist for real? That's an interesting question. Thank you. Well, I don't have any real conflict of interest. Sometimes you would hear people like, if I had a quantum computing, post-quantum computing business, I would tell you, oh, maybe in 2 or 3 weeks, so you should buy my post-quantum crypto. Maybe if I was an academic looking for public money and grants, I would also say, yeah, 5 years. But I don't have this kind of conflict of interest. My perspective, based on the information I have and based on the people I've talked to, and when you talk to researchers behind closed doors, they sometimes have a different opinion than when they talk to journalists. And I think we're very, very far from a universal scalable quantum computer. In other words, from a quantum computer that could break RSA and other crypto. Why? Because it's extremely hard to go from a few qubits. So what we have today is maybe of the order of 50 qubits, and systems that are stable for maybe a few microseconds, depending on which technology. So we might be talking nanoseconds or microseconds, maybe up to milliseconds, but I don't think we're that far. And it's extremely complex to create, let's say, a network of thousands or millions of qubits that would work reliably, not just for milliseconds, but for minutes or hours or even weeks. And when you talk to researchers, they might say, oh, maybe we will reach the quantum supremacy in a few years. Quantum supremacy means the day when we will have a quantum system doing something faster than any classical computer. It might just be solving a problem with 50 qubits that cannot be solved efficiently classically. But reaching the point where we have something that could break the crypto, I don't think I will see it in my lifetime. I wish I will, but I think it's very unlikely. So that's just my personal opinion on this. Thank you for answering my question.
Do you have any?
So the European Commission announced that they're going to spend 1 billion euros on quantum computing research. Do you think anything will come out of this research? Is it money well spent? Or? Because there was this professor that said basically quantum computing is impossible because at some point we will hit decoherency and the error rate is non-linear, so it's going to be, it's theoretically impossible, and all the research papers are actually fakes because they work on small scale, but they're never going to scale up.
Yeah, there's this type of opinion by very respected people. But I think the research, the good thing with research is that you always learn something, even if you don't find what you expected to find. Maybe you have learned something, like the case of LHC, they didn't find what they want to find. So it's a PR disaster, but maybe in terms of knowledge, they learned something. So yeah, I don't have any real opinion on this. Maybe I would spend the money differently. Well, from what I've seen, the public investment from the European Commission are not only motivated, but what we would like them to be motivated. But that's maybe a political question. Maybe one last thing, just small commercial plug. I will be selling a bunch of my books outside during the break. So if you want to get one, I'll be there. Okay, my phone is ringing. Other questions? Yeah.
Thank you. Really amazing talk. So I have a quick question on a serious topic. Where do you position yourself on the whole discussion of cryptographic backdoors, trapdoors, key escrow, and so on? And how do you think, or how do you feel that the developments that we will see in the next couple of years will lead us to?
I think the government should have access to all our data. I mean, if you don't have anything to hide, then well, no, I'm kidding. I don't have no strong opinion on this. There are some technical arguments, some political arguments, and people sometimes confuse the two fields. I don't think having backdoors is good generally, but crypto is just part of the problem of data collection and surveillance. And if you look at Facebook, they don't need backdoors to get your data. They would just give you a free VPN, and that's it. But I've been working on crypto backdoors, and honestly, I've been just for the mathematical value. I've been trying to create ciphers with backdoors, and it's difficult. So typically, the backdoor will not be in the cipher. The long story short is that if you create a backdoor in the cipher, it will, most of the time, there will always be a way to find the backdoor. So you will have to use kind of security by obscurity, hiding the fact that, well, hiding the technique, the backdoor technique that you're going to use. But theoretically, if you look, for example, at the case of Philippe T curves, if you want to create a backdoor, you need some kind of degrees of freedom. For example, if you manipulate constants. And if you want to manipulate constants, you need some degree of randomness. And I don't think there's a simple way to create a reliable backdoor that will not attract the attention of anyone, which might be a good news for people who are against backdoors. Yeah.
So just about the previous question, is there a way to make a secure backdoor, like some kind of secret sharing scheme where the users have their own secret, and the government has like a master secret that it's the only way to decrypt it's like the only other way to decrypt the data except for having the personal secret that you use to encrypt it?
So yeah, you're referring to a class of techniques, for example, the key escrow mechanisms where the government somewhere they have a super master key in a safe protected by armed guards, and that nobody will use unless you need it. Well, the objection of many people to this is that it's very hard to manage. And the objection is that at some point, someone will behave dishonestly, and instead of using this key to only decrypt, for example, terrorist information, they will use it to decrypt the data of political opponents or other people. So I think the argument is fair that you cannot trust human people to protect secrets. And personally, I don't think it would be a good idea to have this kind of construction, because if things go wrong, then it might go wrong for everybody and might reduce your security instead of protecting it.
So it's not a technical controversy, it's like how much you should trust your government.
It's more an operational problem. It's not necessarily trust into specific people or group of people. It just, I don't know, if you work in a big company, and it's difficult to manage stuff. People go in and out, people have different motivations, And protecting secret keys, given the value it has, yeah, I mean, you see in the US how politics work. It's too complicated to have this kind of system. Well, from my perspective, but if in smaller organizations, for example, in companies, you typically have, for example, some key escrow mechanism where 3 or 4 guys use some secret sharing scheme to hide a master key of the company, and the emails of the employees are all encrypted with this master key. And if for some reason a judge needs access, they can use the master key. So in this case, it's a bit less sensitive because it's not necessarily personal information, and it's a much smaller group of people, so it's easier to manage. But at the scale of country, I think it's too complicated operationally.
Thank you.
Yeah, the purpose of this question is to make everyone else feel good, because it's a stupid question. But I paid the parking, so I'm going to ask it anyway. When you made the example of the Ethereum collision on a public key of 64 or something like that.
Yeah, it was a risk, yeah.
Right. Sorry, from an ignorant point of view, I thought it's much easier just to hack any of the wallets that there are. I see many just login passwords after all. Is that true, or is I'm oversimplifying, or it's out of the topic? And does everyone else feel good, by the way?
No, but actually not a stupid question. So maybe you mean hacking the wallet in the sense of guessing the password of the user, or finding user that has a weak password? Yeah, so that's a fair objection. There's been a lot of phishing attacks, and but in this case, you don't need the interaction of the user, so you can do it completely offline. And in terms of password security, I think not really an innovation of blockchain platforms, but something that they do relatively right, is force the users to use a strong passphrase. So if you use the normal way to create an account, you will get a long random passphrase that has a guaranteed entropy of maybe 128 bits. So by default, you will not have the possibility of choosing 1, 2, 3, 4, 5 as a passphrase. And when they give you this passphrase, there's a mechanism to ensure that you've copied it safely somewhere, and you will not lose access to your funds. Because there's 2 problems for wallet security: is first, ensure that only you have access to your account, and second, ensure that you still have access to your account and that you don't lose your passphrase and you don't lose all your money. And that maybe was one aspect where blockchain people are doing a relatively good job.
You talked about this post-quantum ciphers, or like property for crypto, and that there are already some problems that are proof that they will be solved with post-quantum computers. So my question is, what about the other ones? Has there been a lot of research, for example, for those hash problems? Or is it like, yeah, not so much research has been done, and it might be also broken in some years?
Oh yeah, good question. Because you might, like, today just invent a new problem out of the blue and say, this looks post-quantum. So the problems that are used, they've been known for many, many years to be of the type of problems that cannot, or that are very unlikely to be solved by quantum computers. If you look at code-based crypto, at lattice-based crypto, and multivariate equations, these are all fundamentally based on NP-complete problems. So the class of problems for which we are fairly confident that they cannot be broken by quantum computers. So it's like the case of P-equivalent P. We don't have any actual mathematical proof that is the case, but we have a good enough understanding to be very confident that it's secure. In the case of hash function, it's a little bit different, because hash functions, they do not work based on a mathematical construction. They just work by doing a bunch of XORs and additions and bit shift and bit twiggling to create something that looks random. But breaking hash functions with quantum computers, is also very unlikely to work, because the problem that you want to solve is to invert the function, so go from the output to the input. And what we know is that it's kind of equivalent to the problem of quantum search. And the problem of quantum search, we know that it will get you at most a quadratic speed up. So instead of going from the impossible to the possible, it will only go from something less slow. So if you have an output size of 256 bits, instead of taking of the order of 2 to the 256 operations, it will be 2 to the 128. So you remain the exponential domain. And we're also fairly confident that it cannot be improved. So long story short, we have a good level of assurance. Maybe from my point of view, the biggest worry will be in practice the safety of implementations, and in particular against side channel attacks. But that's another type of problem.
Is there other questions?
Oh. Well, I don't know. Okay, thank you for listening, for the questions. And if you have other questions, I will be around this morning. Thank you.